This lesson deals with load line analysis and a piecewise linear model for a diode. You can find these notes in the ECE302 ebook in Chapter 2 starting on page 29. In our previous videos, we took a look at iterative guessing and trying to solve a particular problem. We're going to take a look at a graphical solution next. As we've seen, diodes are nonlinear devices. What that means is that if you had a linear circuit, if you doubled all of the independent sources, then you double the response. And that response could be any voltage or any current. But that's not true for diodes. What does that imply? We therefore can't use any circuit theorems that are based on linearity. For example, Thevenin's theorem, superposition, mesh and node equations by inspection, or phasor analysis. There's a little footnote here. And it says, fear not, there is a way to still use the analysis techniques of ECE302 and 202. We'll have to do that very carefully, and we'll take a look at that in this section. Technically, for nonlinear circuits, all you can use is Kirchhoff's laws. The next method we'll take a look at is what's called load line analysis. This technique can give you a lot of insight as to how a circuit operates. To illustrate the load line analysis, let me do a linear circuit problem, numerically and then graphically. Got two resistors in series with a battery. I want to find the voltage across this resistor and the current through it. Well, because they're in series, I could use voltage divider. The voltage across the 1K is 1K over 1K plus 2K times 12, and that's 4 volts. Knowing that this is 4 volts, then I can find the current by dividing by 1K. So that's 4 milliamps. Let me do the same problem graphically. Let's break this circuit into two pieces, this piece and this piece. And let's write the equations for each of these pieces in terms of V0 and I0. Let me go around the loop. The rise in voltage equals the drops around the loop. But because I out is flowing in this direction, the drop is plus to minus this way. V out is equal to minus I0 times 2K plus 12. I'm going to plot I0 on the y-axis and V0 on the x-axis. So let me solve this equation and put it into that form. I'll bring this on the other side of the equation. It comes a plus 2K times I0, then bring this over here as a minus V0, and then divide by 2K, and divide by 2K. We have the equation of a straight line, where y is equal to mx plus b. What about this circuit element here? Well, let's find V0 and I0 in terms of this part of the circuit. But that's just simply a resistor, so I can use Ohm's law and say that V0 is equal to 1K times I0. But again, I want to plot this on the y-axis and this on the x-axis. So let me solve for I0. It's going to be 1 over 1K times V0. Still an equation of a straight line. Y is equal to mx, but b is equal to 0. This is the slope, and this is the intercept. Now let's graph those. This equation is simply a line that passes through the origin with a slope of 1 over 1K. When I have 2 milliamps, I have 2 volts. When I have 3 milliamps, I have 3 volts, and so on. This other equation is the equation of a straight line, as we mentioned. Let's plot this equation by using its intercepts. So if V0 is equal to 0, I0 is equal to 12 divided by 2K, and that's 6 milliamps. That's this point right here. That's just one point on a straight line. Then if we go back to the previous equation and we set I0 equal to 0, then V0 is equal to 12. And that corresponds to this point right here. If I just connect those 2 points up with a straight line, that represents all possible solutions for this left-hand part of the circuit. This represents all possible solutions for the right-hand side of the circuit. They intersect at one point. And that's the point that's common to the two of them. And that is the solution to our equations. And that is 4 milliamps and 4 volts. We can apply this same technique to a nonlinear circuit. What we can do is segregate the linear parts and the nonlinear parts. This was the example we were doing on page 22 with SPICE. We also did by hand by iteration. Let's write the equations for this circuit. The rise in voltage is going to be equal to drops around the loop. But because, again, the current's flowing as indicated here, the drop is in this direction. V sub d is equal to minus ID times 1K plus 5. And again, I'm going to plot on the y-axis the current of the diode and then this on the x-axis. So let's solve this equation for I sub d. Put this on the other side of the equation as a plus 1K times I sub d. Bring this over here as a minus of d and then divide by 1K. And again, we have the equation of a straight line. Now with SPICE, for eta equal to 2 and I sub s equal to 2 nanoamps, we had this graph. I plotted it again. And on top of this, I sketched the linear circuit that's to the left of the diode. Let's use the intercepts to sketch this pretty quickly. So when V sub d is equal to 0, we have 5 over 1K, which is 5 milliamps. That's this point. Not the answer, just simply one point on the line. And then if I let I sub d equal to 0, V sub d is equal to 5. And that corresponds to this point. So it's connected up with a straight line. They only have one point in common. This is all possible solutions of the diode. This is all possible solutions of our battery and resistor, and they only have one point in common, and that's the solution. What I try to do with a ruler is measure this as accurately as I can. I got 0.76 volts and 4.3 milliamps. And then with SPICE, we found that the voltage was 0.75360144. Of course, that's not exactly the same number, it was pretty close. And that the current was 4.246 milliamps, and of course that's very close to that. So it's really as accurate as your ruler is in doing it. Now obviously this is not the fastest way to solve a problem, but it does give you some insight as to what's going on when things begin to vary with time, and we'll take a look at this in the course. In terms of terminology, this line that's here represents a load for the diode, called a load line. Now what's interesting here is that if you look at that circuit on top, we found the voltage here, and we found the current over here. But this voltage here is also, go back to the schematic, that's the voltage if you were to take the diode off. In other words, the current would be equal to 0. That was this case here. So that represents the open circuit voltage that we talked about with Thevenin's theorem. And then we found the 5 milliamps of current from this equation by setting this equal to 0. That's the same as saying we put a short circuit here, and the current that flows is 5 volts divided by 1K. So this is the x-axis intercept, and this is the y-axis intercept, and this corresponds to the open circuit voltage of our circuit, the linear part of our circuit, and this represents the short circuit current of our linear circuit. Let's generalize these results. What it's going to do is save us some time. We don't have to write loop equations and solve for parameters. We can just simply find these intercepts by inspection. Let's develop an algorithm. First thing we're going to do is remove the nonlinear element. In this case, we had a diode here. Now, our circuit that was left over looked like a Thevenin equivalent circuit, but this could have a lot of batteries, resistors, current sources in it, whatever. You don't have to Thevenize it. You simply have to find the open circuit voltage and the short circuit current. So the open circuit voltage is the Thevenin voltage, and the short circuit current is the Norton current that we talked about in ECE302 and 202. So this is done pretty quickly. We can just simply look at the schematic, open and short, where our diode is, and we can find the results. One more point here. In ECE301 in Chapter 3 on page 58, we show that the ratio of the open circuit voltage to the short circuit current was equal to the Thevenin resistance. Once you calculate these two, we can actually calculate the slope of the curve we had on the previous page. Now obviously it's got a negative slope, so we're going to put that in there too. Early in the chapter, we looked at a voltage controlled amplifier and talked about the need for a DC model for a non-ideal diode. Let me propose one in the following way. Let's take a non-ideal diode between anode and cathode. Let me model that with an ideal diode and a battery equal to VD on. What I'd like to show is that if you plot the voltage across the non-ideal diode and the current through it, you get the following VI characteristic. That when the current flows at a fixed voltage of VD on, and when V sub D is less than VD on, you have no current. Now why would that be true? Well, when I sub D is greater than or equal to 0, this ideal diode is a short, and V sub D equals VD on. That's this part right over here. What happens when the ideal diode is off? Well, let's solve for the voltage across it. If this is off, then the voltage across it is less than or equal to 0. Let's go around the loop this way. Now think of this as just part of the loop. The rise in voltage of the ideal diode is equal to the drop V of D minus VD on. This is this equation right over here. Now that needs to be less than or equal to 0 for the ideal diode to be off. Just solving this equation over here, we get that V sub D is less than or equal to VD on. Let's think of it this way. If you were to set VD on equal to 0, this would move over to the origin and we get the ideal diode back. Now we're able to model a real diode with a piecewise linear model. Now this isn't perfect. The actual curve, of course, is exponential and has a slope to it. But this will be an approximation to get us close to the answer, and then we can refine that with SPICE. Let's revisit this example we did on pages 22 and 31. We found the operating point of this circuit by iteration, by using PSPICE, and then by using a load line. Let's even solve this problem by replacing the non-ideal diode with a piecewise linear model. In order to do that, we need to know what is VD on. Let's just say 0.7 will be our default value. If we know more about a particular diode, well then we'll refine this, but if we don't know anything about it, we're just going to assume it's 0.7. We'll take this non-ideal diode out, replace it by an ideal diode and a battery. Since 5 volts is greater than 0.7, I think current would flow in this direction, so I'm going to guess that the ideal diode is a short circuit. So guessing a diode is a short circuit, what I need to do is show that the current is greater than or equal to 0. Here I've got two batteries, so I've got two node voltages, 5 volts and 0.7, so their difference is the voltage across the resistor, and that's the current in the diode. That's 4.3 milliamps. Is that greater than or equal to 0? Yes. And a voltage across the diode is what we assumed it to be. Now we know from our exact answer that it was 0.75360144. Again, this is very precise, but the current that we solved for isn't all that different from what we did with the iteration or with piecewise. So this piecewise linear approach will get you close to an exact answer using just some of the techniques we learned in ECE 201 and 202. The result will be pretty good if the voltage sources in your circuit are much bigger than VD on. Our textbook refines this model a little bit more by putting a series resistor in. It actually uses the value of R sub D. The value of R sub D for most silicon diodes, small signal applications, what we're going to be looking at in the course, is pretty small. It's on the order of ohms. Including this does give us a more precise answer, but in some problems it can become quite tedious. In this last example, it wouldn't have been a big deal. But when you have a lot of components and you add an extra resistor instead of a voltage source by itself, it does make things a lot more difficult. So what we're going to do is keep the model as simple as possible to do our designs and make our design decisions, and then if we want an accurate result after we design something, we'll run SPICE and see what the results are. And this is load line analysis in a piecewise linear model for a diode.